So I am Chris Parsons. I work for. Dawns on me that I've used a smaller font than I could have. If I'd known the size of the screen, I'd have made the most of it. Anyway, so I'm Chris Parsons. I'm a developer advocate for IBM. My role basically is to go out and work with our customers and our partners that are trying to use Power Systems and Power AI to get the most out of their AI workloads. So a lot of my role involves standing up and doing things like this and talking to you guys about artificial intelligence, machine learning, and then also kind of rolling my sleeves up and getting my hands dirty and actually writing some code and doing some code samples. So this session, there we go. This is Google, by the way, it doesn't work. Anyway, so what is this talk? So this talk's split into two parts with a 15-minute break in the middle. The first part is going to be an introduction to machine learning. I'm going to talk about designing and building infrastructure for this workload specifically. What is Power AI and why is it differentiated? And then go through a few use cases, actual customer use cases, and then also places where you guys can go out and start to find opportunities to do this within your own organizations, within the community, based on my experience and what I'm seeing. But before I go on, I'd quite like to profile the room. Is anybody in the room a data scientist? Okay, maybe a half hand. Okay, anybody in the room a developer? Cool, better. You guys are my people. Right, so what I'm going to do, and I know that this is a bit brave for the technology industry, but I'm going to go through a worked example of what machine learning is and how that differs from the kind of traditional programming paradigm, right, that we're all familiar with. If you have never coded anything and are not a data scientist, do not worry. By the end of it, you'll be an expert in both. So let's start with what is machine learning and how does machine learning differ from programming? Now, programmers in the room, you will know that the first thing you typically write in any programming language is hello world, right? Fundamentally, your challenge is to make it say the string hello world on the screen. In fact, that's pretty much all they teach you at university, and then they release you into the wild and expect you to be able to go and build applications. Hello world is great, right? It's a simple challenge, you see the result quickly, and then you can build it out and expand on those core concepts. The problem is, in the machine learning space, hello world doesn't work, right? If I tell the computer what to say back to me, it's not learned anything, right? It's not AI, it's my intelligence. So how do you translate that gap then? What is the hello world for machine learning? What is like a simple problem that we can all use to get our heads around what is going on here with this technology? There is this data set. This data set is called MNIST. There are a few laughs in the room for people that are very familiar with MNIST. MNIST is 65,000 handwritten single-digit numbers. Now, they're all grayscale, they're all 28 by 28 pixels, and they're all appropriately labeled, right? What do I mean by labeled? Well, I mean all of the numbers of 1 are in a folder that is called 1, right? It's that complicated. So you've got this data set, so 65,000 of these numbers. And they're all there for you, and they're all kind of handwritten like this. This is an example of 4 of them. And as programmers, if I said to you, right, your challenge is to build me an application that recognizes the number 1, and all number 1s will look like that one, right? That's really simple. You can do that really quickly, right? That's not a complicated problem. In fact, you could probably do that in the next sort of 50 minutes of this talk. But the problem is, not all number 1s do look like that, right? There's a huge variation in the way we draw number 1s. In fact, there's a huge variation in the way computers draw number 1s, right? Think about the number of different fonts on a computer. So even typed number 1s don't necessarily look like that stereotypical number, right? And I know if you had infinite developers and infinite time, you could build a system that could recognize every potential number 1. But a lot of the people that I talk to don't have infinite developers or infinite time. But they've still got this same problem. They've still got this problem they want to solve. And it doesn't matter whether or not we're trying to recognize handwritten number 1s, or whether we're trying to recognize what breed of dog something is, or what type of car it is, or whether this is a pedestrian or a lamppost. The fundamental principle is the same thing, right? What we're going to do is expose our system to all of the number 1s, there's about 8,000 of them, and all of the other numbers too, the 0, the 2, the 3, all of those numbers, and ask it to tell us what patterns there are in the data, right? What fundamentally makes something a number 1. And we're going to get the system to do that on its own. We're going to get the system to learn how to do that on its own. So let's go a bit deeper then. So let's explore one of these number ones, right? And hopefully this won't come as a spoiler to anyone in the room, but computers can't see at all. So the computer does not perceive that number one as we do. It sees it as this, right? So this is the pixel values, and it's not quite a one-to-one relationship, but over here we've got 0 representing our white space all the way up to 1, which is our deepest black, right? What we're going to do is say, look at all 8,000 of those that I have already told you are number one, right? And tell me what patterns there are. Tell me what number ones have in common. What makes something a number one, right? And then repeat that for the 2, 3, 4, 5, 6th number. And that's why it's the same paradigm for whatever we're trying to solve, whether or not we're trying to detect credit card fraud or classify different types of dachshund. It's the same fundamental principle. What we're going to do is look at everything I told you was a dachshund, was a number one, and tell me what it had in common. And how the computer does that is this. Now, I'm not going to go into the maths here, and the lines aren't showing up, which is vexatious. But what we've got over here is these x values. These are our input. Sorry, camera guy. I'm going to move back over there in a second. Over here, these are our input pixels, right? Then in the middle, we've got a matrix multiplication. So we multiply each of those input pixels by these weights. And the reason we do that is it lets us assign different priority to different pixels in the image, right? So think about a number one and a 0, for instance. The pixel that is dead center of that number one is really significant, right? Because it's probably the middle of my number one. But the pixel that is dead center of a 0, I don't care about. It doesn't tell me anything. It's just going to be white, right? So I do this massive matrix multiplication. Then I add a bias value to it just for fun, do a linear regression, and at the other side, what I get is my output pixel values, right? What the computer determined that output pixel value would be. Now, this is a significant thing, right? So we've got here the green bubbles are a matrix multiplication. NVIDIA realized several years ago that they'd been designing and architecting GPUs to do exactly this workload. Not for machine learning, right? For doing computer graphics. And if you think about computer graphics, it is a matrix multiplication problem, right? This screen here is a matrix of pixels, right? So it's something they've been doing for a while, was building GPUs to do matrix multiplication. And they said, okay, let's move into this space and start to design GPUs specifically for artificial intelligence. Let's start to design and architect GPUs specifically for AI. And they did. And then they ran into a problem. And that problem was PCIe, right? And what they realized was it didn't matter how quick they made their GPUs, eventually data sets were going to get too big to fit on one GPU, and they were going to need to talk to each other, right? And when they talk to each other, they have to talk over PCIe, which is the standard interconnect, or certainly was a few years ago. And that hurt their performance, because suddenly you had these really quick GPUs talking to each other fairly slowly over some slow electronics. So they came up with their own technology. They came up with this technology called NVLink, cunningly named, which lets you link two NVIDIA GPUs together. Now, it's a physical wire. You can physically plug them in, and then they talk to each other over this much quicker wire, and everything happens more quickly, right? So when you're doing machine learning problems, you get a huge speed up. But then they ran into another problem, and that problem was that if they did that, if they used NVLink, there was still a bottleneck, right? Because the CPU, the processor that moves the data to the GPUs, so the CPU that's responsible for moving my number one over to the GPUs, right, still talks over PCIe. So it doesn't matter how quickly the GPUs all talk to each other, my bottleneck is one stage further out. And this is where the OpenPOWER Foundation came in, right? And the open source power processor. So what it enabled us to do was this. So as you can see on this chart, we've got these NVLink lanes. So I might have a pointer. Yes, look, so we've got these NVLink lanes here that connect the GPUs together. Now that's available anywhere NVIDIA have their GPUs. What's unique to power systems through the open innovation at the OpenPOWER Foundation is we've got this Power 9 CPU here, our latest processor, and then the NVLink to the GPUs, right? So we've alleviated that bottleneck. So we literally can get the data to the GPUs at 10 times the bandwidth, right? So when you've got a GPU problem, like machine learning, like matrix multiplication, this architecture can get your photo of a number one from main memory across the CPU and into the GPU at a much higher rate. And we've intentionally tried to marry these up. You'll notice this is 170 and this is 150. We tried to make those as close together as we possibly could, just so that we didn't, introduce another bottleneck somewhere else, right? Because it's pointless having this communicate at 300 gig a second if this is only at 170, right? So we tried to make those, we tried to introduce parity there where possible. So we've designed this architecture from the ground up, and this is kind of what Power AI is, and I'll come on to that a bit later on, but we're designing this architecture from the ground up for these machine learning workloads to get the data to the GPU as quickly as possible. Now, back to my machine learning hello world. This is what I get out the other side. Does that show up? Maybe it doesn't. So this is what I get out the other side of my machine learning, right? Once it's done the machine learning. I appreciate it's a bit difficult to see. I apologize. But what we've got here, concretely, is a graphing of the weights from 2 charts ago, those green bubbles. If you plot them on a graph, it looks a bit like this. And this is what the computer is looking for when it sees this number. Now, what I think is interesting here is if you look at the 0 up there, I think, yeah, okay, the blue bit there kind of looks like a 0. Fair enough, machine learning, you've done a good job. And the 1, that looks pretty much like a 1. If someone drew that on a piece of paper, I'd say, yeah, okay, I'm looking at a number 1. But what I think is really interesting about this chart is if you look over here at the 4, that doesn't look anything like a 4. And 5, I'd say, absolutely not. I've never seen a 5 that looks anything like that. And that's because the computer is not trying to draw the ideal number 4 or the ideal number 5. What the computer is saying is everything you showed me and told me was a number 4 had this in common, right? It had these regions in common. So all it's doing is looking for those commonalities in the data. And that's what lets you tackle those hugely complex problems without spending millions of man-hours on it, right? Millions of man-hours trawling through images, trawling through credit card transaction data, because the machine can look at that data and intrinsically spot those patterns in it. And then you can use that, so when a new number 1 or a new number 2 comes along, you can say, okay, which does it look the most like? Which of these does it look the most like? And use that to make intelligent decisions and classify those images. So machine learning really is a paradigm shift in the way that we can use computing to solve these really complex problems. And that's why I think in the industry in general, people are adopting it really widely, is because it lets them solve the problem they either couldn't before or would have been too complicated to solve. So that is what is machine learning, with a slight segue into OpenPOWER. What is Power AI? So we didn't stop there. We didn't just stop at the hardware design. We went one tier higher up as well, and we built this. So we went out there to the community, to developers, to data scientists, and we said, right, what tools are you guys using when you go and build AI, right? What do you code your applications in? What frameworks are you using when you build these AI systems? And they came back to us with the likes of TensorFlow and Caffe and Keras and PyTorch, all of these open source tools. This is what the developers and data scientists wanted to use. And we said, okay, we hear you. So we took these frameworks in-house and we optimized them to take advantage of the Power hardware, to take advantage of the Power Systems architecture that I showed you a couple of slides ago, and then we made them all available for free. So all of this good stuff, all of the tool chain that developers and data scientists are currently using is available, all packaged up, ready to run on Power Systems. So this is kind of the direction we're heading in. So we're designing the architecture specifically for AI, and then bringing those frameworks, bringing that tool chain along so that it runs on top of this platform. So it's all about enabling that innovation and making it as accessible as possible to get the most out of this architecture. By the way, there'll be a lot of people that think, yeah, well, what's the value in this if I only want one of them? If you ever try going through the process of installing one of these, particularly from source, like a lot of data scientists have to do in the wild, you'll know that it really sucks, right? It's not fun trying to install one of these and all of the dependencies that come with it, because they rely on so many different mathematical libraries under the covers, which is why it's really useful to have them all come along at once with all of their dependencies in one package. So that's Power AI, but we've also done some cool other tricks, like this. So there's a photo of a server in the middle of this chart, and this is a value add that we've created called distributed deep learning. So we noticed that there was a problem, right? And this problem arises as you try and scale your workload. So here we have one server, and you'll have to use your imagination here, right? I need you to imagine that I have more than 7 photos. Those photos are slightly larger than the little dashes that are going to appear on this slide, right? But imagine this. So we are doing machine learning, and we need to build a classifier that will classify different types of dog. Our process is as follows. We take our photo of a dachshund, our CPU, and we copy it over to the GPU, and that's where the floating point maths happens, and it decides what the weights should be. It does the machine learning about that dashend, then sends the result back to the CPU, and then requests the next image. Now, as you can see through my animations, that took a long time, right? And we're a clever organization, and what we think is, haha, I'm going to buy 2 servers. Brilliant, everything will speed up. The problem is it doesn't, right? The problem is it doesn't speed up, and the reason it doesn't is suddenly my problem's got a lot more complex. I still have the 7 photos of dashends. I still have the same network. I'm still using the same tooling, but now I've got to deal with the fact that I've got to make communication out over my physical network, right? Out over that infrastructure. And then I've got to get the data into another server, right? And things can, in theory, at this point, slow down because everything gets more complicated. The problem space gets more complicated when I introduce more servers. So we realized that and wanted to create a solution to this problem. So we created a library called Distributed Deep Learning, which is available today, that fundamentally overcomes this problem. And it overcomes this problem by running your workload in the ideal configuration, right? So it knows what network topology you've got. It knows what systems you've got. It knows how many GPUs there are in those systems, what memory you've got, how many cores there are in those systems. And then it determines when you hit run on your job, how many nodes to scale it to. Whether that should run on 1 GPU in 1 node because it's really small, or whether it needs to scale to those hundreds of nodes. So distributed deep learning helps you scale your workload. And to prove that, I've animated the dogs to move slightly faster in this chart. So there we go. That is conclusive proof that distributed deep learning works. Some people are looking at me a bit skeptically. Fair enough. So on the next chart, hopefully, yes, here we go. So this is actually distributed deep learning. These are the actual numbers behind my slightly faster moving dashends. So what we've been able to demonstrate here, now this is the same workload, but on 2 different sized architectures. So on the one side, we've got one system. Running our workload took 16 days, right? 16 days is a long time to wait for anything. Certainly for your machine learning job to finish. I wouldn't want to sit there and check if it finishes. And then on the other side, because we've been able to scale pretty much linearly using distributed deep learning, we're able to do that same workload in 7 hours. So you're able to get to those results faster. You're able to get to those insights more quickly. And again, all of this takes advantage of things like the NVLink connection between our CPU and our GPU, our ability to do I/O and to scale these workloads. So distributed deep learning really can make a difference there. Now, we didn't just solve the distribution problem, we solved another problem too. And this is my single photo won't fit on my GPU, right? So this is large model support. So this is where a single bit of data, a single image or something like that, doesn't fit on GPU memory. It's too big for that problem space, right? So think, large satellite images, other kind of medical images particularly that are bigger than the 16 gigabytes I could potentially get on a GPU, right? Now, what I do in a traditional environment here is I copy over 16 gigabytes of the image, and then do the computation on that, get the result back, and then send over the next 16. Or I might try to drop the resolution, right? The thing is, with large model support, what we're able to do is, and there's a talk on this later on, by the way, which I encourage you to get to, because of our NVLink between the CPU and the GPU, because of that architecture designed for this workload, what we can do is copy the data over to the GPU much more readily, right? So we can copy it over in smaller chunks. And that enables us to solve some problems that you simply can't do on other architectures, like this. So this over here, on the top left of this chart, is a scanning electron microscope of breast cancer tissue. And the sites that we are looking for, the sites our clinician are looking for, are these ones that are surrounded by green boxes, right? So they're pretty small, even in this image. Now, over here, for reference, I've put the standard input file sizes for TensorFlow and Caffe, and they're expecting images that, for a certain model, that are 1,000 by 1,000 pixels, right? That's the standard input size, is 1,000 by 1,000 pixels. Now, this image over here, I mean not this one here on this slide, but the actual version of this image is 70,000 by 60,000 pixels, right? So now I've got a problem. My picture, my scanning electron microscope image, definitely won't fit on the GPU, and it also won't fit in these 1,000 by 1,000 boxes that I'm expecting it to go into. So what can I do? How can I enable this? And this is what large model support enables you to do. It enables you to solve this problem without dropping the resolution of the image. Because of course, if you were to drop the resolution of that image, you'd lose the bit you were looking for, right? Because of course I could drop this down to 1000 by 1000, but then I end up with like a blurry mess. I can't really see anything. So it enables you to overcome these problems too. So large model support, which is enabled by that infrastructure interconnect, really does let you tackle these challenges. So that's large model support. Is really, really cool, and there is a talk on it later on, which I encourage you to go to. This is the result, by the way, not just photos of Dashens. So this is a result of using large model support and maximizing that interconnect. So we've got the same GPU architecture. On one side of the chart, we have it running on x86, and on the other side, we've got it on AC922. Now, they're the same, the GPUs are identical. It's the same 4 GPUs in both systems. One of them, because of that faster interconnect between the CPU and the GPU, we're able to run the workload in 49 minutes. The other side, it takes 3.1 hours. So it really is about enabling that speed of delivery, but also tackling those problems that you couldn't somewhere else. And this is a standardized workload as well, which it says down here in grey font that you can't see. Yeah. So, what about actual machine learning then? So I've been talking about deep learning use cases and scaling and things like that and image recognition, but actually 90% of enterprise data doesn't sit in that space. 90% of enterprise data isn't images, and lots of the clients that I'm talking to now are moving that way. They want to start using alternative data sources, but for now they're saying, actually, do you know what? We've got an absolute ton of, column and row based enterprise databases. How do we deal with those? How do we deal with those problems? So we have this tooling called SnapML. SnapML basically looks at taking the 3 most popular, the 3 most prevalent machine learning algorithms. So we've got logistic regression, linear regression, and support vector machines. It looks at taking those 3 algorithms and accelerating them for GPUs. So those algorithms are not GPU accelerated anywhere, other than here in SnapML. And we thought, well, our architecture is all about GPU acceleration. So what if we did the work to make it so that these workloads ran on a GPU as well? So we did, and then we made it available as part of Power AI as well, so you can get your hands on these. And to use them, they're a lot like using sklearn, which is so scikit-learn, which is mentioned over here. So their implementation actually is very familiar to data scientists. We've not done anything wild. There's not really a different way of defining things. It feels very familiar if you've done either of them. And this lets us do something really cool. Now, there is a data set out there that is 1 terabyte in size, and it is the Criteo Labs data set. Is anyone familiar with this data set? Basically, Criteo Lab provide those web banner ads, and this data set is click-through data. So I think it's a prediction on how likely you are to buy a product based on your behavior before you click an advert, one of their banner ads. So it's actually really useful to know if you work in web advertising, the likelihood of someone buying something before they reach an advert, and then you can determine which ad to show them, right? There was a record for solving this problem. It was a record held by the guys at Google, and they used 90 x86 servers to solve the problem. And it took them an hour or so. We ran the same workload on 4 Power 9 systems, the OpenPOWER derivative systems, and this was the result. So we've gone here. It's the same accuracy, by the way. We get to the same test loss in both cases. So this is the hour that it ran on x86 CPUs, and this is the minute and a half that it took using SnapML, taking advantage of that GPU acceleration. Right? So this to me is like a seismic difference between these two. If your competition are doing things in an hour and you're able to get those results and iterate in a minute, I think it stands to reason the advantage you're going to gain, right? It's obvious to me anyway, the advantage you'll gain in being able to respond that quickly to changes in the market, to update your data set that quickly, to retrain your model and redeploy your model based on new intelligence in a minute and a half rather than an hour. And that's what this architecture enables. And that's what this platform enables. So it lets you tackle the problem you couldn't do before, right? Because you might think, well, an hour, it's not worth us doing it. It's not worth us rerunning that because it's going to take too long to get the insight. But this really does let you tackle those problems differently. So SnapML is really, really cool as well. Sorry, yes?
Did anyone try to profile both the platforms and see where it was spending its time?
Yeah, so hang on, how do I go back? There we go. Yeah, so the fundamental difference here is this is using TensorFlow, I believe. Yeah, it is using TensorFlow. But the the logistic regression classifier isn't GPU accelerated on one side. No, no. And that's the difference between that and SnapML, is that we have GPU accelerated those frameworks, those models. So that's kind of the pivot there, is that, so I can tell you this is spending most of its time waiting in the CPU, and this, we're able to offload the workload to GPUs. So it is fundamentally doing things differently, which is why we've got such a colossal speed up. Does that answer your question? Good question, though. By the way, I should have said right at the start, please feel free to fire questions at me. It's much more fun for me if this is interactive, provided I know the answer. If I don't know the answer, don't ask the question. Yes, Tony? Yes, it's part of it. So it's bundled in Power AI. So if you install, yeah. So if you install Power AI, you get SnapML. It's in there. It's part of the package with all its dependencies. Good question. So, yes. Those numbers may exist. I don't have them. You're right. That would be a good comparison to see. But no, I don't. Good question, though. Thank you. So, I want to talk a bit about use cases with the time we've got left. How I think the differences people are doing, where they're going to find these workloads, what they're doing differently now, and also a few cases that I've actually seen. So the first one is we had and there was a spoiler because I skipped on too many slides. We had a bank come to us and they said, hey IBM, we've got a problem with fraud. And I think we thought, yeah, okay, cool. Not the first time we've heard that in the financial services industry there is an issue with fraud. But they said, actually, our problem with fraud's in a really interesting place. We said, okay, tell us more. And said, what's common for us is people will steal your credit debit card, then they will steal your PIN number, and then they will go to a cash point, an ATM, and they'll withdraw money, right? They'll withdraw the funds. And this is costing us, billions of dollars that they're taking all this money. How can we prevent that? How can we stop that at source? How can we stop that kind of fraud at the ATM? And we said, well, we think we can take advantage of the ATM camera to fix that problem, right? So what we did was we built them this system. This guy's an IBMer, by the way, not a criminal. What this system does is it detects whether or not you are trying to hide your face. So in this case, he's clearly wearing a mask. What happens at that point, using the ATM camera, what happens at that point is we recognize he's wearing a mask, and we're in a position to send one of those two-factor authentication texts. Is this you withdrawing cash or not? So should you wish to withdraw cash wearing your favorite balaclava, you still can. You just have to respond to that text message or something like that. And they're using that to prevent fraud at the actual ATM, at that cash point, right? And I think that's really interesting. And I think that's what I'm seeing a lot in this space, is clients and customers and people that are doing machine learning are starting to look at alternative data sources, right? Other sources for this information, or other ways they could get this intelligence. So it's not about thinking, well, hey, what data do we have, right? It's about thinking, what problem do we need to solve, and what data do I need to go to get to solve that problem? Right? So in this case, the problem was, well, people are committing fraud at ATMs, so the data you need to go and get is a bunch of faces of people using ATMs, right? So it's not about, hey, what we have is all this transaction history, and we can use that to identify it. It's about thinking about the problem first, and then identifying ways that machine learning can be used to solve that problem. I have a couple of other videos for you. The first one over here on the left-hand side of this chart. This trailer was built automatically. It was built automatically from something like 3,000 hours of series footage. What it's looking for is scenes of excitement, entertainment, things like that. And it's automatically then generated this content and generated this trailer, right? So this means to that production company that they don't need to spend thousands of hours trawling through every single second of footage to produce this video to entice people to watch their show. So they can produce many more trailers, they can produce better trailers based on that sentiment as well, and it's all pulled together automatically. And if you've ever done any video editing, you'll know how great the idea of having it happen automatically is. So that's how they're doing it, that's how they're transforming their engagement with us, I guess, the consumers of television, of this digital media. and it's literally just look through those, looking for excitement, entertainment, that kind of thing, and pull together that trailer, which I think is really good. Now this one, over here on the right-hand side of this chart, this is really interesting. So what we've got here is a face detection workload that you might be used to seeing. So we're looking for, in this case, different basketball stars. I know nothing about basketball, the way I will hold my hands up and admit that. But we're looking at these basketball stars, and then we're able to do something very clever. So we can count the number of seconds they spend on screen, and then you can use that to determine exactly how much their advertising space or something like that would be worth, right? If the player's on screen for longer, then it's worth more to Nike, Adidas. So we can literally offer that statistic. The other thing is, as well, if you are a marketing agency, is that this type of implementation, this implementation of technology, lets you see how much your spend is worth, right? So I'm giving 2 athletes exactly the same amount of money. This would let me see how much time one of them versus the other one spends on screen, right? So I'm able to target my advertising budget more effectively. It doesn't just have to stop at faces, by the way. We could also look at, the wider scene, right? What other information is there in that image? The actual ads around the stadium, for instance, start to look at those alternative data sources and pull that stream in to find new revenue streams. Right, so I'm no longer looking at, well, an advert cost me X million and then my sales went up by a bit. I don't know if that's because people saw the advert or I released a new product. I don't really know what's going on. And it's about generating that actionable intelligence by using alternative data sources. And I think really that's kind of where we're heading. By the way, both of these were built using a tool chain that I will show you in the second half of this talk. So please come along to that if you want to see how these were built. I will show you how they were built and how easy it is to implement an application that uses either of them. So stick around for that. Now, with the final 10 minutes or so, I want to talk about, I might stop that from playing before we all go mad. Put that logo up, or maybe that's a bit biased. There we go. Go back to a random slide. I want to talk about use cases, right? The places that I think people can get started with this today. For me, there are 3 obvious places, because I think throughout this talk, I hope it came across that actually one of the difficulties with machine learning is that you could really tackle any problem you had if you wanted, if you had the data. And that's a difficult thing to get your head around, right? Because as an industry, we're so used to being told, well, these are the really specific things this technology can do. So if you want to do one of those, brilliant. Otherwise, look for some other technology. Whereas to turn around and say, you can do anything you want, what hurts you the most is a different way of thinking. And oftentimes, I'll find that actually that can stall for a while, because you think, well, if I can do anything, I'm going to want to boil the ocean. I'm going to make things really complicated, and I'm not even going to know where to start. So where can you start looking for these solutions, right? Where do you start looking for these use cases? For me, there are 3 obvious places. The first is anywhere where you're collecting data, right? Anywhere where you're going out there and you're getting data. What if you did it differently? What if you didn't use a web form, for instance? What if you used a more engaging, a more exciting way of collecting that data? And there are companies doing that. I was going to say, has anyone bought car insurance? Hopefully anyone that owns a car puts their hand straight up. So, car insurance. I'm sure we've all been through the process of buying it, right? You go to that website and you enter every single piece of information about your car ever, what colour the wheels are, who was in it last weekend, and it takes you 4 or 5 days. You enter all this information, and out the other side of it, you get a price back, right? And it says, okay, well, this is how much your car insurance would cost. There's a company in the US that's doing that slightly differently. They've built a platform where what you do is you walk outside to your car and you take a photo of it. And then from that, it gains all the information that it needs to determine the age, make, model of the car. It knows where you are, of course, as well, and it'll give you a quote for your car insurance, right? It's about thinking about collecting that data differently. And think about it, where are you going to go? Are you going to go to the platform where you take a photo of your car and you get a price back straight away? Or are you going to go to the place that means you lose your bank holiday weekend filling in all these different forms, right? It's a no-brainer. You're going to go back to the place that gives you the best experience, and machine learning really can do that. So that's the first place, anywhere you're collecting data. What if you use speech data? What if you used image data like that? The second place is process optimization, right? Those things that people don't enjoy doing. This is about, I think, going and talking to the boots on the ground, the people doing the jobs day to day, and saying, what sucks up 80% of your time, but you don't enjoy doing, right? That problem. What do you do that you actually weren't hired to do and it takes you forever, right? And that's an ideal place for machine learning. Because the chances are, if they don't like doing it, it's because it's easy and it's mundane. And if it's mundane and monotonous and they spend forever doing it, chances are that a computer could learn how to do it too. There's another startup in the US, and the reason it's US-based is the two-party consent for recordings thing. Anyway, so there's a US-based startup that has built an application for CRM, the customer relationship management, where instead of asking your field sellers to come back to base and then fill out all this information saying what clients they spoke to, what they spoke to them about, all of this data, what it does is it pulls that in from their calendar. Right, so who's in the calendar invite, what the agenda was, pulls in all this data to fill in this application. And then it goes one stage further in that it will listen to the phone calls and then determine what the client was interested in based on the sentiment of that conversation. Maybe they said they were interested in product X, not product Y. And it'll pull all of that in. And then maybe they said when they were going to look to buy. Maybe they said, hey, we're going to look to buy in November, December. It'll pull that in too and then notify that seller when he needs to see that information, right? And if you think about that as a tool, which are you going to use? Are you going to want to use the one that means you spend forever filling in this information, or are you going to want to use the one that does it automatically and tells you when you need to action something, right? It's a no-brainer. You're going to do the one that saves you time. What about field engineers going out there and actually, climbing up energy pylons to inspect the cables, right? What if you just fly a drone over it? And that's quite a prevalent use case, actually, is to fly a drone over it, use that image data to see whether or not you need to send that field engineer up there. And that improves safety, it improves the amount of time your employees spend up that energy pylon, and it makes that whole process, I guess, more effective, more efficient. So the first is, anyway, you're collecting data. The second is any of those mundane processes, an ideal opportunity for machine learning. The third one, and this is absolutely my favorite one, is the opportunity to kind of preempt your user's next action, so to know what they're going to want to do next, and offer it to them on a plate so they don't have to go and look for it, right? The simplest example of this, and we've seen this for years, so this won't come as a shock to anybody, the simplest example of this is when you book a flight with an airline, and it says, you're in this country for these days, do you also want a hotel, right? Fairly obvious example, didn't require any machine learning, but machine learning lets you go one stage further. My favorite example of this is Gmail, actually. So Google realized that they had, they looked at the data, right? And it turns out loads of people were starting emails and then never actually sending them. And they thought, okay, well, why are all these emails going to draft, right? So they did some research, they brought in some focus groups, and they looked at why so many of their emails were going to draft. And it turns out that it's because people didn't know how to start the emails. So they'd write the name of the person they wanted to reply to, and then go a couple of lines down and then write nothing. So they thought, okay, how can I solve that? And if, by the way, you're thinking, well, I know how to write emails, I can promise you I don't. Every email I've ever written starts with the phrase, I hope you are well. And then a bit below that, the email I actually wanted to write is there. It's because I don't know how to start emails, so I would be one of their cases. Anyway, so they looked at using machine learning to solve that problem, right? They looked at using artificial intelligence to solve that problem. So what they're able to do now is using AI is understand the context and meaning of the email you've received, understand what questions you've been asked, understand the syntax, understand potentially your relationship to the person that sent it, and then it will come up with 3 smart replies, they call them, a positive, a neutral, and a negative. And those are the first sentence reply to that email. And they've had this huge upsurge in A, people using this service, and B, email traffic being sent using it, right? Because it offers you what you need to do. It takes away that pain point, makes it easy to do what you want to do next, which is reply to that email. And as an end consumer, where are you going to go? Are you going to go to the service that means you have to start every sentence with, I hope you are well, or are you going to go to the place where it helps you over that hurdle, helps you solve that problem, and gets you to where you want to be much faster? So those are the 3 places for me that I look for machine learning use cases. 1, anywhere where you're collecting data. 2, any of those business processes, right? Please automate them. Please make things easy for your employees. And the third one is anywhere where you can get ahead of your users and offer them stuff on a plate. And that will keep them coming back, right? And that will drive your user adoption and stuff like that. So that's it from me. Thank you very much for listening to the first half of this two-part talk. In the second half, I'm going to get hands-on, I promise, and we're actually going to show you some code, which is really cool, and we're going to go through actually building and training and deploying one of these AIs for image classification workloads to an iPhone app, funnily enough. So thank you very much for listening.